Let's work through a couple examples now from start to finish using Gaussian elimination to solve our system of equations. Okay, we can start by writing the augmented matrix 6x minus y equals 2 as one row, and x minus 2y equals 4 in the other. Now we know that we need to start by getting a 1 in the top left corner, and we notice that we have a 1 down here in the bottom. So we understand that we're allowed to switch 2 rows in the matrix, but make sure that when you switch those rows, you bring the entire row up. The 1, the -2, and the 4. 6, -1, 2. The whole row goes to the bottom. Now that is the one step that if you forget to label that one, I'm a little bit more forgiving because usually I can figure out what you did. Okay, some of the others might seem obvious to you, but I have no idea what you attempted to do or how you got where you went next. Remember that once we have the row the way we want it, meaning starting with a 1, we just recopy it and we're done with that row and we don't change it ever again. After I have a 1 in the top left corner, I want to make a 0 here where the 6 is. And that's where we're going to do the elimination part of this. If we recall that this means we have 6 x's, and I want to eliminate, then I'm going to need the opposite of positive 6, which is -6. -6 is what I'm going to multiply everything in row 1 times. And after I've multiplied all of these numbers by -6, then I'm going to add them to the row of numbers below. And again, while I'm doing all of those things, I'm not going to take the time to write out everything times -6 and line it up with the other row and then add them all together. Okay, this is the shorthand version of that. Meaning -6 times 1 is -6. -6 plus 6 is 0. -6 times -2 is 12. 12 plus -1 is 11. 4 times -6 is -24. Plus 2 is -22. You should be able to do that without writing a bunch of things down, or officially without poking a lot of buttons on your calculator, but I know most of you will go there. After there's a 0 down below, now we want to work on this 11, and instead of an 11, I want to turn it into a 1. Since there are no rows below to switch around with, now we get to do our division. Okay, you could write it times 1/11 if you would like to, but it's okay to write it in terms of division as well. 0 divided by 11 is 0. 11 divided by itself is 1. And -22 divided by 11 is -2. This is as far as I have to go with these smaller systems, a 1, and then a 0, and then a 1. So now I'm ready for my back substitution. The bottom row says y equals -2. Equals -2. I'm not really sure what I said. Okay, the top one says x minus 2y equals 4. So we substitute -2 in for the y, we solve for x, and find out x equals 0. Last, we write our solution set as an ordered pair. You can check your work, plugging it into both equations if you want to make sure you've done everything correctly. Okay, this one here is a little bit different because neither of our rows start with a 1. Okay, when that happens, the rule is still that we work from left to right. And so what that means, unfortunately, is that we're gonna be stuck dealing with fractions. Okay, but there aren't too many numbers to deal with here, and we'll be okay. We're looking at halves or thirds, so we should be able to handle that. Because there's no row that starts with a 1, we can't just switch places with 2 rows. So then our next choice is let's multiply or divide everything in the row by a number. Dividing by itself, meaning 3, gives us a 1. Now, since I have a 2, positive 2, on the bottom, and I want to turn that into a 0, that means in order to get a 0 there, I need to multiply the top row times negative 2. The opposite of positive 2 is negative 2, and then we'll add it down. So negative 2 plus 2 is 0. Positive 2/3 and 5 would be 15, and 2 would be 17/3. And negative 20/3 plus 3/3 is negative 17/3. Most of the systems that we work with in our textbook have nice integer value solutions. Not all of them, but most of them. Which means we should see some common numbers and factors here as we go along. Now to get a 1 here, where the 17/3 is, we can either write down that we're dividing everything in that row by 17/3, or dividing by 17/3 is the same thing as multiplying by 3/17. But 0 times or divided by anything is still 0. Dividing 17/3 by itself gives me 1, and negative 17/3 by positive 17/3 gives me a negative 1. So the bottom equation says 1y equals negative 1. I have a lot of room, so I'm going to write down here. The top one says x minus 1/3 y equals 10/3. The nice thing about this is that they already have a common denominator. Okay, we can keep our cool and make it through these. A negative times a negative makes a positive 1/3 here. So this says x equals 9/3. 9/3 is equal to 3. Our solution set then here is 3, negative 1. I have 2 more that I want to cram in to this video. Let me see if I can make it a little bit there. Okay, and these are our special cases. So I want you to pause the video, play with them for a minute, figure out how you know it's one of the special cases, and see if you can determine what the solution set is from there. Right, on the top one, we already had a 1 in the top left corner. So when we go to make the 0 where we need it to be, then not only does it turn into a 0, but so does the number next to it. Now, if we have more rows to deal with, we'd say, well, that's not that big a deal. We could slide that down and come back, deal with a different row. But if we end up with a 0 where we have to have a 1, and we can't switch anything, any places with any other rows, okay, then we know it's one of our other 2 cases, either a no solution or a dependent systems case. Okay, so what happens over on this side of the equal sign is what determines that. Notice the bottom row, when we turn it back into an equation, it says 0 equals 0. Since that's a true statement, we say, well, I know that means there's an infinite number of solutions. So then from my top row, I can pick a letter and solve for either x or y. It will always only be one step to solve for x, because you have a 1 there. So x equals 4y plus 2, and y gets to be its own name. And here's our infinite number of solutions. On this example here, I said, well, I don't have a 1, so I'm going to divide everything in the top row by 3. And then I'm going to take the top row times 9 and add it to the bottom row. And the same thing happens here on this side to the left of my equal to, my divider bar here. I have a 0 where I need a 1. I can't fix that, so I have to stop by looking at what the other side says. Okay, that second row says 0 equals 30, which is not a true statement, no matter what ever. So who cares about the top row at this point? I can stop right there and say this system is inconsistent. or I can say that there's no solution to that system. A row of zeros is always one of our other special cases. If it's zeros all the way across, that means I have a dependent system. And if I have zeros on the left equal to a number on the right, I know that's my inconsistent system.